Hi, I'm Bita Azari. The title of my paper is EmoStyle, One-Shot Facial Expression Editing Using Continuous Emotion Parameters. Throughout history, psychologists and researchers tried so hard to find representations for emotions. In 1960s, Paul Ekman proposed 6 fundamental human emotions, and these emotions were happiness, sadness, anger, fear, surprise, and disgust. He later on added 2 more emotions that were contempt and embarrassment. But also, so many other researchers proposed different ways of categorizing emotions. One of the other ways of representing emotions is using 2 continuous values of valence and arousal. Valence shows the positivity or negativity of an emotion, and arousal shows how mild or intense an emotion is. The values can be from -1 to 1. We can see in the circle on the right that valence is the horizontal axis and the arousal is the vertical axis. For example, excited has positive valence and positive arousal, and anger has negative valence and positive arousal. The goal of our project is to have an input image and then a target emotion that is represented with valence and arousal, and then have the output image representing that emotion. We want to preserve identity, pose, background of the input image. In past, there have been many researchers trying to do facial expression editing. Mostly they use generative models. You can see here Ganimation, VS*GAN, and XPR-GAN results. They mostly have artifacts and they generate images in low resolution. StarGAN is one of the most popular generative adversarial models. It has high performance in face generation and the results are high quality images. It also has a very rich and disentangled latent space. That's why it's used for facial editing. Here you can see some of the methods that use StarGAN as their backbone. They were not specifically designed for emotion expression editing, and also the control over the outputs are not that high. You can see here the results of GAN space, interface GAN, and style flow. We also proposed the StarGAN base model. It consists of 2 phases. Phase 1 is training EmoExtract, which is to disentangle emotions from other facial attributes in the latent space, and the second phase is fine-tuning the StarGAN 2 generator to ensure the high-quality reconstruction of the real images. Here's our model architecture. To train EmoExtract, we have 2 steps. The first step is emotion variation. We have an input image and a target valence and arousal that are random, and what we want is an output image representing the exact same person with the same background but with the desired valence and arousal that we chose randomly. In the second step, we don't have the random valence and arousal. We only have the input image and we have an emotion recognition model that detects valence and arousal of the input image. The output image should represent the exact same person with the same emotion. This helps us have high quality reconstruction of the input image. To train EmoExtract, we use different loss function. One is emotion loss. By using this loss, we try to figure out if our output face is showing our desired valence and arousal. The next one is identity loss. We use a state-of-the-art facial recognition model to preserve the identity of the person in the input image. The reconstruction loss is used to enforce high-quality images. This one is used in the second step of our EmoExtract training. Pose loss is used to preserve the pose of the input image, and for achieving that, we use a subset of landmarks that are estimated by Facial Alignment Network FAN. You can see this subset of landmarks that we chose in the image part C. And lastly, we have background loss. For background loss, we estimate a mask on face excluding background, ears, and hair, and then we use reconstruction loss on the mask region. You can see the mask region in part 2 of this image. By doing so, we can preserve hairstyle, skin color, and background of the input image. In phase 2 of our project, we fine-tune the StarGAN, so it can work on real images. Here we have EmoExtract frozen, and then we try to fine-tune the StarGAN generator. The input here is an image and a random valence and arousal, but the image is a real image, not from a StarGAN domain. The output is a real image which is showing the desired valence and arousal. We tested our model with 1,000 images with their corresponding latent codes. We also compared our model with GAN space, interface GAN, stall flow, GAN mood, L2L. We used FID and LPIP score to measure the diversity and the quality of the generated images. To evaluate our framework's identity preservation capability, we employed an external facial recognition model and calculated the cosine similarity between the original and edited images. We also compared the diversity of facial expression in our method with prior work by calculating the standard deviation of valence and arousal. You can see in the table EmoStyle outperforms other methods in FID, LPIPs, and ID preservation, while maintaining high valence and arousal standard deviation. Here you can see the outputs from GAN space, L2L, and our method. Both L2L and GAN space models fail to preserve identity in some emotional expression. Here is another set of examples which compare our model with stall clip, GAN animation, and GAN mood. These methods can handle real images with varying degrees of emotion intensities. The images on top represent the input image, while the rows of images illustrate different intensities of emotion generated using various methods. As shown in this image, all three struggled to effectively synthesize the desired emotion in a given image, and they were unable to maintain the identity of the original image. It's worth mentioning that GAN animation and GAN mood generate images at 128 by 128 resolution, and others generate images at 1024 by 1024 resolution. We also did another set of experiments, which were ablation study. We did ablation study on different components of our method. We tested EmoStyle without different loss functions, and the results showed the importance of each component in our method. You can see in the image and the table that each component were important in our model. Here are some sample outputs of EmoStyle. Each output corresponds to a different combination of input, valence, and arousal. The results align with our expectation as they effectively convey the positivity or negativity and the level of arousal of the faces. And here are some of the samples of real images that were made to GIF so that you can see the continuity of our facial expression editing. In summary, the contribution of our paper were we posed a semantic editing architecture for high-resolution facial expression synthesis within a continuous emotion space. The results are high-resolution 1024 by 1024. We were able to maintain identity and other facial attributes while editing facial expressions. We proposed a tuning method to edit real images, and we were able to generate plausible outcomes from only one image of a face. Thank you for your attention. Here you can see the QR code to EmoStyle project page and Rosie Lab webpage.